Yeah, it's now recording.
Okay.
Hello, everyone. I am very happy to welcome you to another meeting of AI in Robotics Reading Group. Today, we have with us Samarth Brahmbhatt. Samarth is currently a researcher at Intel. Before Intel, Samarth got his PhD in robotics and computer vision uh, at Georgia Institute of Technology, where he worked with James Hayes and also Charlie Kemp. A lot of interesting work that he has been doing involves actually understanding the perception, uh, or understanding the notions of interactions with hands and objects, particularly for manipulation and grasp. And today, Samarth is going to talk to us about topics in hand-object contact. So take it away, Samarth. All yours. Thank you.
Yes, thanks for inviting me. I'm very happy to present all this work, and especially we have some very recent work from CVPR 2021. So I'm also excited to introduce that. Um, but the overall theme of my talk is going to be hand-object contact, as you can see in the title. And while I am currently at Intel doing a postdoc, most of this work was done while I was at Georgia Tech, also during an internship at Facebook Reality Labs. So yeah, let's go right in. And I want to talk about a couple of data sets that we have generated in this field of hand-object contact uh, and associated data modalities. And then I want to present very quickly some insights about human grasping behavior that we have found kind of interesting and surprising that emerged from this data. And then I'm going to talk about various methods that we have developed for contact modeling. Let's motivate this a little bit. Why do we want to study hand-object contact in the first place? So we, at least for me, the main motivation has been to understand hands in action. You can see this image and you can see that someone is holding a camera, but also you probably know that they are intending to take a picture with the camera based on how their fingers are touching the camera at the button and so on. And I believe that if building on top of recent advances on object detection in images, object pose estimation, which I've seen a lot of great work recently, if we can, in addition to that, understand hand object contact uh, and also hand pose and things like that, it can open up a whole new way of communicating with computers. So then you can imagine that any kind of physical object lying in the environment around you can be converted as a computer interface device. You can just interact with it, you can touch various locations, and if the computer is able to understand the meanings of those touches, that will convey information to the computer. For example, you can have very, uh, very easily and cheaply 3D printed pianos, for example, and then you can just run your fingers at various locations and start composing music that way. Now, that is far into the future, but I think understanding contact is going to be an important part. And it can also, I think, help in other things. For example, when we want to design robotic hands, it might be useful to consider the kinds of contact patterns that the human hand is able to exert on daily objects. Uh, and when we want to design grasping algorithms, especially for robotic hands which are multi-fingered and dexterous and kind of close in their structure to the human hand, we can get some inspiration from how humans grasp objects by looking at the contact patterns. But my work, the thing that I'm going to present today is mostly going to be focused on understanding hands in action. So yeah, let's first start with some data, right? We all want to do machine learning on for hand object understanding, and we of course need data. So we have introduced two different data sets. The latest one is called ContactPose, which was presented at ECCV, and then that was building on top of some fundamental things that we introduced in the ContactDB dataset that was from CVPR the year before. And just to start out, I want to give some examples of the kind of data that you can get in the ContactPose dataset. Here's an example from the dataset. So we have high quality 3D models of 25 objects that people use in daily life. And they are annotated with many grasps. And each grasp is represented, the hand in each grasp is represented using these kinds of 3D joints, which are expressed in the object coordinate system. And the hand and object are also sort of tied together through this contact annotation, which is the texture on the object surface that you see here, where more yellow means higher contact, and it's a continuous valley of contact between dark blue, which is no contact, and then very bright yellow, which is high contact. And since we have these 3D joint locations, we can also use recently developed, embodied hand models, for example, the Mano model, and fit them to these 3D joint locations. And we found that doing so is meaningful because it allows us to do some better machine learning when it comes to contact prediction. So we also provide the parameters for fitted Mano hands along with each grasp. And along with each grasp, we also have a large set of grasp images. So all this data was generated by capturing videos of participants holding these objects and waving them around. And subsequently, we track the object through the entire video. So you can project all the information, the hand joints, the object pose, into each of these images. And these are images taken from 3 different perspectives, as you can see. And later on, I'll kind of quantify how much of this data we have. To compare this with some existing data sets, this is actually a very active research field, and we have seen some very interesting data sets come out recently. Mostly image-based. So, for example, the first one, second one, and third one that you see here, they capture the hand pose and object pose using either magnetic trackers in this first one called first person hand action dataset, or using some complex optimization methods in this third one called the Honotate dataset. And then there's the Fry hand dataset, which also uses optimization methods to kind of recover the hand pose. So the interesting part is that these kinds of image-based algorithms typically lack contact annotations because it's almost impossible to observe the surface of the hand that is touching the object using a traditional camera. And I just want to mention that the ContactDB dataset that I talked about before is sort of a subset of this because it contains just the contact annotations and doesn't contain any hand pose annotation. And to capture contact, researchers have used things like gloves that participants wear on their hands and then grasp various objects. And we find that actually, at least we believe that it would be useful to have the hands sort of unencumbered and not altered in appearance, so that easily deployable machine learning algorithms, image-based algorithms, can be trained on that data. So in contrast to this data set, the ContactPose data set kind of offers a unique combination of annotations where we have these high resolution contact on the surface of the object. We also have the hand pose and the various images. Uh, but at the same time, we lack realistic object textures because we 3D print our objects, and I'll come to that later. Um, and we also lack real world backgrounds of these images. uh, Actually, we found that you can kind of while doing data augmentation, you can actually mask out the background and kind of just put any random images. So I think that is not such a big problem, but the uniform object texture is certainly one of the drawbacks of contact pose. But at the same time, doing that enables us to capture this high resolution contact, um, which is a trade-off. All right, so the main technology used to capture contact is thermal cameras. And here I'm showing you the stream coming from three different kinds of cameras after somebody has held the object using their bare hand for some time and then put it on this turntable. And you can see that the data from the thermal camera kind of very surprisingly reveals the contact that happened between the hand and the object, which is completely hidden in the RGB and Dept modalities. And this is the effect that we use to capture contact. So the contact is captured after the grasp. It's not a live capture of the contact, um, but it still offers a, a really good source of contact ground truth. All right, so the we actually chose to 3D print the objects, as you can see here. And there were a couple of reasons for that. First, 3D printing automatically gives us a very high quality object models to work with in our computer vision algorithms. So we know for sure that this object is going to correspond very tightly to the 3D model that we have. I know that scanning technology is getting more and more mature, but I think it's still kind of, there's still some gaps that need to be filled there. Um, and then, yeah, the other reason is that the material that is typically used for 3D printing, it's called PLA. It's kind of a plastic. Turns out it is excellent for retaining heat. So we find that after you hold the object for about 5 seconds, the heat signature stays on it for at least 15 seconds, which is more than enough for scanning it using a thermal camera. Uh, and during those 15 seconds, it doesn't diffuse a lot. In contrast, we found that uh, objects constructed out of metal, for example, metal is a very good conductor of heat, so it very quickly diffuses the heat. But plastic is great for retaining the signatures. So this is the um, kind of the whole capture setup. So we have this frame in which the participant stands, and then this set of 7 OptiTrack cameras are going to be used to track the object pose, which I'll come to that in the next slide. And then we have these 3 Kinects, which are capturing the RGB and Dept videos, the thermal camera, which is looking at a turntable, and the participant, after grasping the object and holding it, will put that object on this turntable where it will be scanned by the thermal camera. So here's a typical video of our data collection process. This is actually me, but the participant basically stands at the threshold, holds the object. The one important aspect is they're instructed to avoid in-hand manipulation. So once they kind of adjust their grasp on the object, they pick up the object from the table and settle down on a particular way of grasping, uh, we actually request them to avoid shifting their fingers after that, because that would basically kind of smudge the thermal prints on top of the object. So this is all the analysis that I'm going to present is for static grasping and not dynamic grasping. So while they are holding the object, they are free to move the object in any kind of arbitrary trajectory. And we run an off-the-shelf hand hand joint detection algorithm called OpenPose in the feed, in the RGB feed from the three different Kinects. So you can see that those 2D joint detections overlaid on top of these images. They are slightly noisy, but since the hand is static with respect to the object, we can hope to average out that noise, and I'll come to that. But first, the object is also being tracked in these videos, and for that we need some markers on the object. Now, the main issue with uh, traditionally how markers have been used for tracking is uh, is you get these kinds of retro-reflective markers which are coated with some special kind of material which is highly reflective in the IR domain, and that is what those OptiTrack cameras are tuned to capture. But um, we wanted to avoid distorting the surface of the object so that we don't influence the way people are grasping. We don't want them to avoid touching some areas or want to touch certain areas. So we tried various combinations and actually settled down on this sort of we decided to use the fact that we are 3D printing our own objects. So we kind of cut these cylindrical recesses in the object surface while 3D printing. And then these hemispherical markers fit nicely into that. And actually, the hemispherical nature is also important for good tracking performance because these markers are typically highly reflective along the surface normal. So if you have a planar, like a planar square of that reflective tape, it is much less effective for tracking. But we found that putting these objects flush with the objects, putting these markers flush with the object surface is a good compromise between uh, avoiding influencing grasping behavior and also tracking those markers robustly. So once we have all that data, the problem of getting 3D joints, 3D hand joints, is one of triangulation, right? So we have multiple images where we have these kind of 2D joint detections, which might be individually noisy, and they are shown by these blue dots here. And we know the object pose. So all we need is to triangulate these 3D locations of the hand joints in the object coordinate frame, and there have been various well established techniques to do that, minimizing reprojection error and so on. And we use GTSAM, which is an optimization framework for 3D data, to do this. And here's a typical result. So you can see, first of all, using these green dots, the object is being tracked. Um, and once you optimize the 3D 3D hand joints with respect to the object coordinate system, you can then transform those joints by the current object pose and then project them into the image. So you can see a typical kind of hand joint annotation also overlaid in these images. So uh, just some quantification of how much data we have here. We have 50 participants who are grasping 50 participants who are grasping these set of 25 household objects. And actually they grasp them twice, once with the intention of using those objects. So for example, you want to take a picture with a camera, or cut something with a knife, or um, or wear those eyeglasses. And then the same set of objects are then afterwards they are re-grasped for handing them off to somebody else. So in total we have more than 2300 unique grasps of these objects. uh, and along with that, with all those videos, we actually have a large set of almost 3 million RGBD images which are kind of depicting these grasps. And oh yeah, I forgot to mention at the start, please feel free to interrupt anytime for questions. But yeah, so these are details about the contact pose dataset, and you can actually go to this website, contactpose.cc.gatech.edu, and there's a kind of an uh, interactive thing that you can use to explore the entire dataset. You can see the contact map, the hand joints, and also the grasp images. And at the same time, we have an API for the contact post data set. You'll find links over there to load the data set for your own kind of machine learning task that you might want to do. And the entire data set is publicly available for download. All right. So that was the data that's going to be used for the rest of the talk. And first, I want to just show some kind of data mining insights from all this data. Um, One thing that we can do is we can associate contacted regions with the part of the hand that was responsible for contact. And I'm not going to go into detail here, but basically you treat the hand as a kind of piecewise linear. So it's kind of like a skeleton. And then you can compute distances from the points on the object surface to the various line segments and select the line segment that is closest. So here I'm showing a color coding of the contacted regions for the binocular. So white means that area was not contacted. But if you have a color, then it is each different color is associated with a different finger. And you can similarly associate different colors to different phalanges, so proximal to distal. And we can use this association uh, to, to, to aggregate over the entire data set the probability for each vertex on the hand to be contacted. So there's a jump between this one and this one. So here I'm talking about the skeleton, but using these skeletons, you can actually fit these nano mesh models using just some very simple uh, L2 distances between the nano joints and the skeleton joints. And so once you do that, you can use the same association technique to associate contacted points on the object surface with points on the hand. And if you aggregate that information across the entire data set to, uh, to just calculate the probability of each hand vertex to be contacted, this is what it looks like. And we are presenting it separately for handoff grasps and use grasps. And this is probably my favorite image from the data set. uh, just these images say a lot of interesting things. First of all, we notice that the thumb and index finger are very important for all the various grasps that we perform. And not surprisingly, fingertips are in general more contacted than other regions of the hand. But at the same time, a lot of contact is happening at the proximal phalanges, various areas of the palm, and things like that. And this motivates the inclusion of these areas in contact modeling and contact prediction software, which which traditionally a lot of this software has focused exclusively on fingertips, but we found that all these non-fingertip areas are also quite important. We also find that not all fingers are equally likely to be contacted. For example, uh, any area on the little finger is less likely to be contacted than all areas on the index finger. And this can inform the design of, potentially inform the design of robotic hands, where you're trying to make the decision whether to include an extra finger or not, because that would entail extra hardware. So if you want to do the kind of grasps that human do, maybe excluding the little finger for if you have some hardware constraints is not such a bad idea, but excluding the index finger would be a big kind of disconnect. And we also see, interestingly, that if you look at just the distribution of contact over the entire hand surface, we see that it is much more concentrated for handoff, and it's much more diffused for use. And this also intuitively makes sense because if you're handing off some objects, it is very simple to sort of just grasp it from the top using your fingertips and give it off. Whereas for using, we already have, well-established ways of well-established methods of contacting particular regions of the object to be able to use that object. So that requires contact in many different areas of the hand. Okay, and the last one, we also performed active area discovery. So this is kind of reversing that contact probability. So now we are looking at probability for various points on the object to be contacted by a particular part of the hand, and the signal is pretty strong for a reasonable set of objects. We see that, for example, if you look at which areas on on the mouse are likely to be contacted by the index fingertip, we see that very frequently the index fingertip is touching this kind of button area. And you can see the same for flashlight buttons, camera buttons, things like that. And just as an aside, I feel like um, thermal cameras and these kinds of analyses could be used for building surveillance, where if you want to figure out which are the surfaces in a room or on a floor that a lot of people are touching with high frequency, uh, probably thermal cameras can give you lots of insights there, and then you can focus uh, sanitation efforts or things like that on those areas rather than going and trying to sanitize the entire room. Okay, so now coming to various methods that we've developed for modeling contact. The problem setup looks something like this. You're given some representation of the object shape. Um, we have we have used point clouds, but I think you can use meshes or other kinds of distance functions and things like that. There are lots of algorithms for 3D processing recently. So given the shape of the object and some information about the grasp, this information could be in the form of the 3D joints, so the hand skeleton, or it could be the mesh of the hand, or it could be a grasp image. This information kind of gives you the context of the grasp, which we hope will enable us to understand the hands in action, right? And then given the object shape and this context, we extract some features which are representing this grasp and associate those features with each point in the point cloud, and then use off the shelf uh, algorithms like pointnet plus plus, or even we've had success using just simple shared two layer MLP, which is kind of just individually applied for each point. So you can use this, you can train these neural network algorithms to be able to predict contact. So this is the problem setup. If you want to do learning with images, then there is one extra layer, which is how do you extract features from the images and how do you convert them to the point cloud features. So we crop the hand object area into a square, and then um using the data that's available, it's pretty easy to kind of uh, segment out the hand and the object area and then composite various random images in the background. And then we use UNet style encoder decoder new convolutional neural networks to extract dense 40 dimensional dense per pixel features for each pixel in these images. And now if these images actually represent multiple viewpoints of the same grasp, then we can use the object pose that is known to us and the camera intrinsics to actually aggregate these features onto the point cloud, right? So for each point in the point cloud, you see where it was projected in these images and kind of just copy the feature from there, and if a point is visible from multiple images, you average out those features. So after doing that aggregation, you again have features associated with points in the point cloud, and then you can use existing methods to predict contact. So I just want to present an example result before going into some details. Uh, so here's an example result from trying to predict contact using images. Using the three images that you see on the left, we can see that uh, it is mostly able to get the like kind of the low frequency details of the contact. Um, if you compare it to the ground truth that's on the bottom left corner. The interesting part is that we found that it is highly dependent on uh, which parts of the object are actually being visible from those images, right? So we actually have results in the paper for predicting contact from a single view image rather than multiple views. Um, but that performs perhaps unsurprisingly worse than if you have multiple viewpoints. Um, and on the other hand, we found that if we include, instead of using the image features, if we use the features derived from 3D information. So here I'm showing you uh, features that were derived from the hand skeleton. You see that it is actually able to capture highly nuanced details. You can see the details around the palm contact, um, and also around the thumb, and the black line segments here actually indicate that we dropped out the features related to that part of the hand, but it's able to recover that kind of missing information. And we have a lot of kind of numerical comparisons in the contact post paper, but here I wanted to kind of present qualitative results. uh, as an aside, we found that uh, there are some representations which make contact prediction uh, easier than other representations. So, uh, so we know that if you just look at the entire data set, the number of points that are contacted is actually uh, is much less than the number of points that are not contacted. So there's a skew in the data over there. So to deal with this skew, we actually found that it was useful to discretize the continuous contact value uh, into 10 different bins and then treat it as a classification problem where the the penalty for misclassifying into a particular bin is inversely proportional to the occurrence frequency of that bin. Um, and this is actually inspired from work in a totally different domain, actually work in the domain of colorizing grayscale images, where I think the problem is similar, where there are kind of very highly skewed data distributions. And we found that using that technique actually helps us a lot and allows us to predict a continuous contact value. So at test time, when you have these kind of prediction weights for the 10 different bins, you can use something called an annealed mean to get a continuous value for that prediction. So that was about contact prediction, and I think the motivation for that was, as I said earlier in my talk, um, if you're getting an image or some other 3D representation of a grasp, uh, it's very useful to understand where the contact is happening. So, and that can drive many different human computer interaction applications. But we've also done some work on contact fitting, which is, given the object geometry and some oracle gives you the contact map, uh, can you actually configure a hand geometry to comply with this contact map? And this is actually a challenging problem because of the high dimensionality. This, for example, I'm showing you a model of the human hand, which has about 26 degrees of freedom. So you want to be able to configure that to fit this contact. And the motivation for studying this problem is for kind of simulation of contact, as well as trying to inform grasping algorithms. Um, and we actually found that this kind of fitting of kinematic models of the hand to the contact map is actually not limited to just human hands. Once you, of course, it will be most optimal if the model that you're trying to optimize for is close to the hand that generated the contact map, but you can try to fit other hands with very different geometries. For example, some robotic hands, the Allegro hand, which has 3 fingers and 1 thumb, or even the Barrett robotic hand, which has a completely different uh, kinematic structure. Um, but this kind of algorithms can serve as a bridge to including human demonstrations in robotic grasping algorithms. Uh, so this is what we did in this IROS paper, where the paper focused on developing algorithms uh, to configure the parameters of the hand to agree with a given contact map, where we did that using an iterative optimization algorithm, which has three different terms. The first one is, uh, given this contact map, we actually discretize it. So we kind of randomly sample various points on the object surface, and depending on whether each point was contacted or not, we kind of binary threshold it into red and green regions. And the idea is those green regions where contact happened is where you want to attract your hand model, and then the red regions are regions where you actually want to repel your hand model away from them. And at the same time, you want to penalize intersection of the hand into the object surface. Uh, and we found that using these kind of 3 terms, and we also have kind of an optional term for encouraging the thumb to always be in contact with the object surface. Um, we found that using these terms we can optimize the hand geometry pretty well, given a good rough initialization. Just to show you some details, um, basically, if imagine if there's an object point pi, and the finger is kind of hovering around it, you can and you want to attract the finger closer to this contacted point. You first solve the correspondence problem, which is the correspondence between point on the object surface and the closest point on the finger. And I'll talk a little bit more about that later. But assuming you solve that correspondence problem, the finger location is actually uh, a differentiable function of the hand parameters. So the hand parameters um, are denoted by phi here. They could be joint angles and translation of the root joint of the hand, for example. Uh, the location of each point on the surface of the hand is a differentiable function of those 26 different hand parameters. And the distance of the object point to that location on the finger is also a differentiable function. So you can actually you actually have this kind of differentiable chain from this kind of attractive cost function to the parameters of the hand, and you can use that to optimize the parameters of the hand. What you see as SDF here is basically sign distance field. It's kind of a trick that we use to uh, increase the speed of computation, but I'm not going to go into the detail here. SDF basically just gives you the distance of that point with any point on the finger surface. So that's the attractive term. You can kind of negate that and use that for repulsion, but there's a particular aspect that you need to take into consideration. So imagine this kind of a scenario where the finger is close to the object surface because it is being attracted by a contacted point, which is shown by the green dot here. Now we don't want the non-contacted point, which is the red dot, to have a lot of influence in repelling the finger away, because the finger is actually not trying to contact that red point. And you can use the surface normal and the angle between the vector from the point to the finger and the surface normal to kind of decide, to kind of of modulate the strength of that repulsive term, uh, which is what we do here. Actually, we have a binary decision. So if the angle is more than a certain value, we kind of turn off the repulsive force from that point. And using these terms, you can do an optimization. You can see this optimization in action here. And we found that this kind of algorithm can generate plausible looking grasps for different kinds of geometries of the hand. You can see some of the results here. Now these results are sort of in the simulation domain and not on the real robot, and I know that there exists a big gap between those two, but we didn't have the chance to address that. I think it would be an interesting area for future work. And uh, and so then all of these things kind of uh, nicely tie together in this new CVPR work that just got accepted to CVPR 2021, which is called ContactOpt, and it's led by Patrick Grady, another PhD student at Georgia Tech, where we developed this kind of integrated framework for doing both contact prediction and contact fitting. So, and it is more tailored towards understanding human grasping behavior rather than robotic grasping. But a lot of the ideas are transferable. So, uh, given an image of someone holding an object, there are lots of really impressive image-based hand pose estimation algorithms, right? So they understand the image and then they give you the 3D pose of the hand with respect to the object. Um, but what they are basically kind of 90% in terms of accuracy, but they're missing kind of the last mile of accuracy. Now that accuracy difference is it might be small when you consider 3D distances of hand joints, for example. But when it comes to contact, these small minute differences actually make or break contact and completely change the contact structure. So ContactOpt is kind of a plug and play algorithm that you can put on top of any image based hand pose estimator. It will first We first use this deep contact, which is a neural network that we trained to take this coarse hand object geometry and predict contact patterns both on the hand surface and the object surface. Uh, and then these contact patterns can then be used in an iterative optimization of the hand parameters to have a hand object uh, interaction which is kind of much more realistic from the contact perspective. So let's look at some of the individual components here, and we are still working on the camera ready and code release for this paper. But you can already go to this website and at least read the paper for now. So first thing is uh, how do we train an algorithm to predict contact, uh, especially when we know that the input to that algorithm is going to be noisy, right? So you're going to have noisy hand pose. It might be penetrating the object. It might be kind of hovering over the object. And we basically took the contact pose data and artificially perturbed it. So we artificially added noise to the hand translation, hand pose, and things like that. And for each of those pairs of object and noisy hand pose, we know the ground truth contact from contact pose. So this kind of gives us almost an infinite data set for uh, training a predictor that will take a noisy input but predict the contact patterns for a non-noisy grasp. So we use that to, and I've already talked about some contact prediction techniques before. So we use that to train this deep contact algorithm for predicting contact. Here are some results from that algorithm. Excuse me. Mm. So you can see that the results are they're not as crisp as the actual ground truth that you get from the thermal camera, but they're more than enough to actually allow us to do the later optimization. And the next part is a differentiable contact model. Um, so um, it is important for this contact model to be differentiable so that we can actually use it as a part of the iterative algorithm to optimize the hand parameters. But at the same time, we know that there are lots of modeling errors. First of all, the hand actually has a lot of soft tissue which deforms, but our hand mesh is a rigid mesh, and there might be lots of kind of small millimetric errors in terms of modeling the object or modeling the interaction between the hand and the object. So we developed this kind of capsule based method where each vertex on the object surface has a small kind of millimeter sized capsule around it, and we say that uh, if any hand vertex is within this capsule, then it is uniformly it is kind of uniformly detected as a maximum contact value. And if the and when there's no hand vertex inside this capsule, then the contact value kind of falls off radially with respect to the distance from the capsule. And so this sort of allows us to model a little bit of the soft tissue dynamics of the hand. I mean, we don't have any kind of rigorous data driven proof of that, but this is kind of an ad hoc way to model the kind of unmodeled errors in the hand models. And then using these capsules, you can get the contact values, and you can use those contact values to um, to optimize for the parameters of the Mano hand model, so that such that the contact map that is generated from that differentiable contact model matches with either the ground truth contact map or the contact map predicted by that contact prediction neural network that I presented before. Um, so using the combination of both of these, this can sit on top of existing hand pose estimation algorithms uh, and allow us to kind of reconcile the contact correctness of those grasps. And here are some results. So you can see in the top row, uh, prediction results from some state of the art image based algorithms or some artificial perturbations added to the contact pose dataset. Um, and then the results produced by the ContactOpt algorithm uh, compared to the ground truth. So in conclusion, I would like to say just a few things that you can do differentiable contact modeling through by using hand object distance. Uh, uh, of course, there's the correspondence problem. So you need to assign points on the object surface to the points on the hand surface, which can be done either through a nearest neighbor search, or it can be done through uh, more efficiently if you can have distance fields pre-computed for different 3D models. And then just want to mention a small thing here. I was looking at some robotic software. So for example, Mujoko, and I found that there are actually some interesting connections between how people in the computer vision community have been thinking about contact and this one. So for example, you find that in Mujoko, when you look at how the constraint for contact is being is being modulated. You see the ability to actually have these different kinds of modulations, where on the x-axis it is how the amount of penetration into the of one 3D model into the another 3D model, and on the y-axis you see kind of the strength of the repulsive force, which can kind of be thought of as a proxy of contact. And yeah, lastly, I want to thank all the collaborators and all the developers of lots of open source software that I've used for all my research. And I'm open to questions.
This was wonderful. We have a few minutes for questions. Does anybody have questions? Or I have a few, but I want to give the audience an opportunity.
I had a question. So I was
Sure.
wondering if you plan to, or if you have already used this data set for some control, like for robot control.
No, we haven't. And I think the maximum that we've done on the robotics front is the work that I presented, the contact grasp work, which is just trying to figure out how to configure these high dimensional hands. And I think uh, one thing that I realized while collecting all this data and also working with various robotic hands is that the connection between human grasping behavior and robotic grasping is the strongest when the robotic hand is kind of very close to the human hand. So for example, like the shadow robot hand or something like that. But if you have other kinds of hands, like just simple open close grippers, then the connection sort of is very tenuous, because for those kinds of geometries a lot of other different strategies come into the play. You can do some grasps which you cannot do with human hands, or vice versa. and and in that case I think
But
it makes it
is it just about the morphology of the hand, or is it also like other modes of sensing and other modes of contact? So even if you have, let's say, an allegro or a shadow hand, which is 4-fingered or 5-fingered, is it just the points of contact that you have five of those contacts, or is it actually like when you grab with your hand, you use other points of contact which are much harder to even plan with? So currently, very few planning algorithms or
Mhm.
learning algorithms exist which can uh, let alone use the other modes of, let's say, modalities of feedback. So touch, pressure, slip from the whole skin rather than just point of contact. We can barely do planning for like whole hand. At best, you can do this sort of like 5-point contact planning. Even that is already hard enough.
Right.
But you're not really using, let's say, the fingers and the surface and other joints of the surface to make contact. But many use cases that you showed in your case, even your data set, will have that, right? It's like grab it with
Yeah.
a grasp that is clasped, right? Or power grasp. That usually uses full surface. It's not like 5 points.
Yeah, that's a very good point, and it reminded me of this kind of evergreen robotics grasping software called Graspit, and they have these kind of predefined models of various robotic hands and a human hand. Um, and actually, if you look at it, the cost function, the kind of default cost function that they optimize for, is they have decided various points all along the palm of the object. Uh, so there's like, it's still not continuous contact all along the surface, but they do have points at various phalanges and things like that, and they're optimizing for minimizing the distance of all those points to the object surface. And that's just one example, but I think overwhelmingly a lot of other simulation software, as you rightly said, focuses exclusively on the fingertips. And I agree that there is a gap over there, but I'm hoping that seeing this data actually inspires people in the robotics community to give more importance to other parts of the hand when we see that it is important for how humans grasp objects.
But I think as a roboticist, I would argue the problem is not that, oh, we don't want to. The problem is most likely we just don't have algorithms that support something like that, right? Like algorithms which can do that level of reasoning or that kind of reasoning is just too tricky.
Right. Yeah.
Either from learning or from planning perspective, right? So that remains to be seen. And then when you get to that, I would even argue another concern becomes, do you want to do careful planning, or do you want to just build in high quality sensing through the hand so that you can have a lot of compliant control?
Yeah. I mean, yeah, when you have
that sort of
sensors,
model,
you can do like kind of live feedback loops and things like that. Yeah. That's
are you continuing to work on this line of work, especially now that you've switched institutions? So like, I don't know if the hardware or all of the setup carried over.
I have shifted to robotics, and I am, all the projects that I'm working on are kind of in progress right now, but I'm not using thermal cameras anymore, but I'm kind of looking more at robotics hardware and things like that. Yeah.
So when you say robotics, is it like manipulation, or is it mobility, or something else?
Yes, one of the projects is for manipulation. Yeah.
Okay.
The details are sort of it's still being decided, and we're still working on it.
Okay.
But I mean, I'm facing all the questions that you mentioned, which is, how do you do all these? Okay, even if you don't have sensors that are spread all across the surface of the hand, can you even do the planning and things like that? And I think those are all good questions. Yeah.
Wonderful. I think this would be a good place to sort of stop and pause this. We would like to thank Samarth once again. I think this was a riveting talk, and the topic seems to be very broadly relevant to a number of people, from continuum robots working on building multilateral manipulators to people working on perception and control. So thank you very much for this. I believe Arthur has set up meetings with a few folks from our end. You will be meeting Mehdi next, and then I think you'll see the signups on the sheet. Thank you again for coming over to chat with us, and hope to see you sometime soon. I hope. Perhaps later after in fall. I guess the summer is still virtual.
Right. Yeah, great. I'm looking forward to it. Thanks for inviting me.
Yes, thank you. Bye.
Yeah, I'm just going to direct message you the link to the next meeting.
Okay. And thanks, Varun. I saw that he sent